Okay, so those of you who saw me earlier today in 220, thanks for your double attention, and the questions some of you asked are very nice too, so appreciate that. Today, we are trying to make things a little bit more advanced and realistic inside Vensim and Insight Maker by actually adding in delays, something we've only so far talked about in the context of causal loop diagrams. So if we think about delays, well, before we get there, let me just make sure everybody's feels okay about lookup tables and converters. We will use lookup tables converters a little bit today, again, to set up some of the inputs. So are there any lingering questions about lookup tables or converters in either of these tools? No? Yeah. Sure. For both Vensim and Insight Makers, are you mean by the two? Okay, just Vensim. Okay, yeah, I can let me pull up Vensim. And all right, so got Vensim up here. A lookup table can go anywhere an equation can go because they're really just meant to be an alternative form of an equation. So let me just grab this thing while I've got it here and pull it back. All right. So the idea here is that if I were to create, let's say a stock, say bacteria, and I've got its flow coming in. And so this is my, net regeneration. Now, this is kind of like the fish example. I might want to make net regeneration depend upon the number of bacteria in kind of a non-trivial way. So I might not have a good formula for it. So normally what I would do, like if I had a good formula for it, is I would connect bacteria to net regeneration. And then I would go into my equations here. For bacteria, I'll just set in a initial condition. Sorry, it popped up the dialog on my other screen. Let me pull it back over. All right, so for a number of bacteria, I'll just say I'll start with 1, that doesn't really matter. And then I go into my net regeneration curve. Save this. My net regeneration function here. Now, normally I could do something like bacteria times some birth rate. I could put in a formula in here. Now, it might be that I don't know a simple formula like this that really represents how bacteria relates to net regeneration. And so this might be, let me see if I can make this a little bit bigger. I don't know if I can make the diagram bigger, but I don't think I can make this one bigger. So I apologize for that. Hopefully, yeah, no, that's all right. So yeah, no zooming here. So apologize for that. But basically, this says bacteria times 0.2. Now, I could say, well, I don't want a linear relationship between bacteria and regeneration rate. I want something else. And I might know some formula. Like I might know that I want like 0.2 times bacteria times 1 minus bacteria divided by carrying capacity. So this regeneration formula is kind of the standard logistic growth formula, and it gives me kind of a hump-shaped curve where once I have 100 bacteria, they don't regenerate. When I have 0 bacteria, they don't regenerate. And in the middle, around 50 bacteria, they regenerate the fastest. But maybe I want something that is, is more asymmetric or has sort of some different shape to it. So instead, what I do is I get rid of this expression, and I go up to a subtype here, and I change it to with lookup. And then I say I want my input to the lookup table to be bacteria. And then I go up to as graph. And then now I can just draw whatever relationship that I want, where my bacteria are on the x-axis and my net regeneration is on the y-axis. And so I can do that by clicking on points. So down here, notice it says x is 0 to 10. I'm going to just change my x max to 100. And then my y max, let's say that I want it to go up to 1. So on the y-axis, it goes from 0 to 1. Well, now this axis basically is a bunch of points that connects my number of bacteria from 0 to 100 to a regeneration rate from 0 to 1. And I can just click anywhere to place a point. So I could say, well, I know that when notice that I'm mousing over here, it's showing my X is at 24, my Y is at 0.25. So let's say I know that when I have 24 bacteria, I have an output of 0.25 regeneration rate per bacteria. And so I could click on that point. I could then click on another point up here. I could say, well, I know if I have, however this many bacteria, 34, it gives me a 79%. I might know there's something weird about my system there where I get kind of these bimodal distributions here. And then maybe I also click down here. So now I've got a regeneration rate curve that for whatever reason, like if I actually look at the data for bacterial regeneration, this might be more realistically what the data show in the lab. So if I were to fit this, I might come up with some kind of hump-shaped approximation for this, and that would be the equation. But if I really want to specialize to I want to study bacteria that have these bimodal pattern where they have high regeneration at one density and at a higher density and low regeneration in the middle. In this weird case here, if I don't have a formula relating bacteria on the x-axis to regeneration rate on the y-axis, I just draw the graph. And that's what the lookup table does. So it replaces an equation with a graph. Now the questions about that, does that make sense? So when I click OK here, it's just going to bring me back to the equation menu. It's going to have all these points written out just so they're reproducible so we can see those points. And then when I run the simulation, or if I run the simulation, it will use this to figure out what the regeneration rate should be. In fact, if I do that, let me just make this input go all the way to 0. And I'll make this go all the way to 100. All right, so it edited those. Now if I click OK, and I click OK here, and so if I try to run this, let's see if I get no errors, so that's a good sign. And then if I go to the graph tool and I graph, let's say bacteria, then I see that, and let me maybe give this model a little more time to run. So it's time step, I'll make it 0.01. I'll let it run till 500. The times don't really matter, but month seems a little weird, so I'll do something else. Run that. And then it actually, on my other screen, gave me a error, which you might see if you play around to lookup tables. And let me bring that error over. And so because I just crafted this lookup table, it's not surprising I might get some errors. And this says lookup out of bounds at 441.29 above net regeneration, computing net regeneration. What that means is that when I plot this bacteria here, if I go to graph, then it's saying that somewhere around 441, which is over here, this regeneration curve goes slightly over 100. And I've only defined the lookup table between 0 and 100. So I didn't manage to pinch the net regeneration down quickly enough to prevent them going over 100. So they go slightly, somewhere around here, it's going to go slightly over 100. See right there, it's like a 100-point fraction or something like that. 100.331. I didn't define a lookup table there. And so that's the reason why I gave you that lookup table out of bounds. So, but it's still kind of like, this is like a weird S-shaped growth curve now. So a nice S-shaped growth curve would look more S-shaped. It could have like nice smooth inflection point or whatever. This still looks roughly S-shaped, but it kind of wiggles in the middle. And that's because I put a non-trivial lookup table in instead of just a mathematical expression. And that's the point of lookup tables, is they allow us to add a little bit more realism so we get curves that look a little bit more realistic and not kind of like mathematical stereotypes. So does that help everybody? Any questions about that? And I could fix this lookup out of bounds error that I got by going into the lookup table and making sure it was defined. So I could go into this equation, go to net regeneration, go to my as graph, and then I might just say, actually, I'm going to make it from 100 to 500. I'm going to make it strictly 0. And that way I really kill, it's defined so that if the regeneration curve ever happens to go a little bit over 100, it'll still have an entry in here. And so now if I go and run this thing, I'll go and simulate. Then I get no errors whatsoever. And if I were to graph both net regeneration, let's say both of these here. So there's my bacteria curve, looks just like it did. My net regeneration, you can't see because the axis goes up to 150. I guess I could just only plot net regeneration, see what that looks like. And so there's my net regeneration curve, and you can see that as time goes over, it's sort of going through these spikes because the bacteria is growing up. And as the bacteria grows from 0 to 100, it's actually sweeping through the net regeneration curve, and that's why we're seeing this hint of the net regeneration curve pop up there. And so there we go. So we're actually seeing the net regeneration curve in action by plotting net regeneration over time. I just want to emphasize this is time, not bacteria. But the net regeneration curve is actually bacteria. Oh, and the other thing I hinted at this last time is one of the cool things you can do in Vensim. If I get rid of this graph and run SyntheSim, I'm now running SyntheSim and there's no sliders, but if you click, in theory, it used to work this way. Well, maybe in the new interface, I have to do this in a different way, but in SyntheSim, you can actually modify these lookup tables live. And so it's not working for me now because I haven't done it in this version of Vensim. Let me make sure. Oh, wait, I see now. There, okay, there it goes. So it was asking me, do I want to overwrite my data, but it's on another screen, I didn't notice it. So now notice that the lookup table is actually shows you a little hint of what that variable looks like. And if I click on this, it brings me the lookup table up. So as SyntheSim is running, I can actually go and insert additional points. And then if I look back at what's going on over here, then as I'm inserting points, then you can see that the bacteria little thumbnail is changing here. So now it kind of rises up, hits a plateau, and then rises again. So you can actually change the lookup table in real time, which is something you can't do in Insight Maker. So that's kind of fun. All right, so that was kind of a longer demo than I was originally expecting, but any questions about that? Well, there's no, you mean like, there's no equation version of this, it's just all the points. Yeah, so as I'm adding more points, it's creating a longer list. And so I think it actually, so like it has notes up here, clear all points and look up, start delete mode, show table. So if I click on the show table here, then I can actually see all of the points. I think there's a way to drag this over. It's a little ugly, but but all of these, however many points, show up right here. So as you're clicking on those, you can see which ones you're adding, and you can actually edit them here as well. So you can try a bunch of hypothetical things and then sort of keep track of what you did. And then you can go in and edit your model afterwards and then make these changes. If you like say, oh yeah, that's the lookup table I want, you could go in and freeze it in the settings. Any other questions? All right. So we'll see lookup tables a little bit more. So I'll just maybe leave Vensim running in the background. And so today you want to work on delays. So we've talked about delays in causal loop diagrams. So we got this simple CLD here. as if I am hungry, I might eat because I'm hungry, but my hunger will not be reduced until later after that food is processed. And so we can say that if for a system like this, what are the causes of those delays and how do we model those inside Insight Maker or Vensim? So the important thing we want to start with is what are the types of delays here? Well, if you think about it, one of the things that causes a delay when you eat food is the time it takes to actually get down the esophagus. So, food goes in, gets chewed up, it forms a bolus, and that bolus goes down the esophagus until it eventually hits the stomach. And it takes a fixed amount of time to get from the back, from the throat down into the stomach. So that's one of the things that we might need to simulate is fixed delays. So something happens in one part of a system, it should happen a fixed amount of time later, but exactly the same way, just shifted in time. So let's see how to do that in Vensim. So the simple thing here is if I just look at the rates, so this is like looking at flows without stocks. So I'll add the stocks here in a second. I can think about the ingestion rate. So that's how the rate of intake of food into the mouth. And then I can think about the rate into the stomach. So this is how quickly food is coming to the mouth. This is how quickly food is coming into the stomach. And one would imagine, or maybe you could think of this as how quickly food is coming into the throat. And so you would imagine that whatever the pattern of food intake looks like here, it's going to look just like that, but a few maybe seconds later as it hits the stomach, because things kind of flow together down the esophagus. And so what we do in Vensim is first I need to sort of simulate food entering the body. And so this is not a delay idea here. This is a lookup table idea. So what I did is I created a shadow variable called time. So it is just a time variable. I made that an input to ingestion rate. And then when I go into my ingestion rate variable, I do auxiliary with lookup, and then I define time over the whole simulation time. And I say that at time 5, the ingestion rate jumps up to 5. It stays there until time 6 and then jumps down to 0. That's what's defined in these numbers here. That's what's drawn here. That's just showing that I've got a pulse of food that comes into the mouth at 5 and then exits the mouth by 6. And that's all that I'm sort of simulating here. So no delays yet, but that's kind of the input to the system. So then I have to go over to rate in the stomach. And this is where we implement the delay. And so I'm going to just say that the food enters the stomach, matching however it entered the throat, but delayed by 5 seconds. And that's what this delay fixed command here is, procedure here is in Vensim. So right in the equations, you do delay fixed, you do the variable that you want to be kind of the source, like, what it's going to match. The second argument is how long of a delay is there. And the third argument, you almost always leave 0, and that's the initial condition. That basically means that when you start the sim, what is rate in the stomach going to look like, because it's waiting for 5 seconds to get its first input from the ingestion rate. That's what this initial condition is. So normally, you just set that equal to 0. If I do that, and then I were to plot both of these things, then I get this. So the blue is the ingestion rate. We can view that as the input. The red is the rate in the stomach. And the blue looks like a box. It starts at 5 and goes until 6. And so the red looks like a box that starts at 10 and goes until 11. So this red box is just a copy of this blue box, but shifted over by 5 seconds. So we need to add stocks to make this a useful model. But this is kind of where we start at it. So any questions about how delay fixed worked here? Everybody see that we created this blue one with a lookup table, and this red one is just a copy of whatever the blue one is, but 5 seconds later. We could have made a lookup table with like a triangle shape here, and then a triangle shape would show up 5 seconds later, and so on. Okay. All right, so we need to add stocks. So now we can keep track of the ingestion rate. Well, the ingestion rate is the flow, where the food in the esophagus is the stock. The rate in the stomach is an outflow from the esophagus and is an inflow into the stomach. So I can take these two flows and make them depend upon each other via delay, and then let the stocks just integrate those. And so that's what I'm doing here. So ingestion rate's got our same pulse of food. Rate into stomach has got the same delay fixed, but I've now inserted these two stocks to connect everybody together. And what happens with that? Well, now, if I plot these things, the green is the ingestion rate. This gray is the rate into stomach. The blue is the stock, food in esophagus. And the red is the stock, food into stomach. So what we can see is that from time 5 to 6, you can see there's kind of a ramp up of food into the esophagus. It's like a block of food that is gradually becoming more and more into the esophagus until the whole block of food is in the esophagus. And then there's no more food to add. So from 6 until 10, you just have the esophagus is full of that block of food, and that represents it going down the esophagus. And then finally at time 10, then we hit the outflow process, which is just a 5-second delay of the inflow process. So now, though, when that's turned on, that's going to pull things out of the esophagus and at the same rate, increase things into the stomach. So all of the material here gets traded and put into the stomach there. And so that is how we can simulate this structured process where food starts in one place, gradually gets into one place, hangs out in there for a while, and then gradually is traded to another place. And we actually are modeling the time it takes to shuffle from one point to another. So any questions about that? Does that make sense? Questions online too? Okay. All right, so we can also do that in Insight Maker, very similar. So I can create a converter in Insight Maker, which is like a lookup table, and a rate into stomach. Same thing I did in Vensim. In the converter, I can make the input time, so I don't need the shadow variable, and do the exact same thing I did in Vensim. That's one way to do it. The other thing that I can do is I can just make this an auxiliary variable, and Insight Maker's got a command called pulse, and it will automatically generate a pulse starting at a particular time, sticking around for a certain amount of time, and then going back to 0. And so I can say this pulse command, I want a pulse to start at time 1, have a height of 1, stick around for 1, and then repeat 0 times. And that gives me this thing here. So that's the same as what we did in the converter, but I don't have to introduce that funny time variable. And it actually turns out that Vensim's got the same thing. It's called pulse train, start, duration, repeat, time, end. Same idea here. And so you can also, instead of using the converter in Vensim to introduce this, you could use these functions. Now, in rate into stomach, Insight Maker has their own fixed delay. In Vensim, it was called delayed fixed. In Insight Maker, it's just called delay. So notice here, there's a list of functions here. This is in the old version of Vensim, or I'm sorry, Insight Maker. When you opened up the equation extended box, these popped up here. Now, all the equations, this equation line is on the side. So when you click on rate into stomach, it shows it on the side, but it will show a little sigma, like a little Greek letter sigma next to it. If you click on that, it will show you all of these functions. And you can go into the historical functions, and that's where it has things like delay. So if you forget whether it's delay or delay fixed, you just go into the little cheat sheet here, this the little sigma, click on that, and it'll show you all of the Vensim functions that they give you. And you go under historical functions to find all the delay functions and other time-related functions. So that's what's going on there. So we got the delay and its arguments. The first one is just the ingestion rate, how long you want it delayed, and then again, it has an initial condition, which you can omit. And that's an easy thing to do. It's just to leave out that initial condition and leave it as default. So if we do that, we get the same output that we got in Vensim. Here's the ingestion pulse. Here's it delayed 5 seconds later. Then we can add stocks. So here's the ingestion pulse as an inflow to the esophagus. The rate into stomach is an outflow of esophagus, but an inflow of food into stomach. Same delay. And then we simulate that and we get exactly the same thing that we got into Vensim. So that's how we do it in Insight Maker. So questions about that? It's the same idea as Insight Maker, but questions about either one. Questions online? Okay, so I've been doing this example with this kind of food and esophagus thing. It's not really a system that we might often, model. So when do we use fixed delays? Yeah, sorry, do you have a question? Mm-hmm. Mm-hmm. Right. So the question was like, do you type this in or do you like select it from a list? Is that what you're kind of saying? Yeah, you can do both in Insight Maker. So you can actually forget that the quick reference exists. And so in fact, maybe it's helpful for me to just show this. So let me bring up an Insight Maker tab. And then I'll just show you bringing up this delay here, if I can remember which side of, there we go. Right, let me drag off a tab so I don't expose sensitive information. Create new insight. So if I were to say create a, two variables, kind of like I was doing before, I want to create a link between them. And then if I go into this one, here is where the expressions are, and it's showing me that I can use the incoming variable as one of my options here. And then it's got this little sigma that shows me these functions. Now I can just type, can go up here and I can type delay, and I can go and type, that I want to use this. And I could have even just typed that myself, new variable, as long as I put brackets around it. And then I can say 5,0, or I could have gone and hit this little cheat sheet here, and then I can go down to historical functions, and then I can select delay, and maybe I should do that without it being populated already. So I'll go here, historical functions, delay, and then it then shows me kind of a template where it's saying that the primitive, that's the thing I want to be delayed. The next argument's the delay length and then the default value. So then I can go in and then manually say, I can either type these things in. So under primitive, I can type new variable because that's the input, or I could have just selected it. Under delay, I can type 5, get rid of this length, and then default value, I could type 0. Or I think with Insight Maker, I could just get rid of it entirely. Does that make sense? Great. Any other questions, Insight Maker questions? Now I have got this up. I see a question on line functions inherit the units of the variable for purposes of simulation. So in both Insight Maker and Vensim, you choose the units, and the functions have to be consistent with the chosen units. So if they're, right now I've just been doing unit lists to keep things simple, but which direction? This way? Yep. But if I would have instead chose a unit here, then I would need to make sure that this new variable, so, and maybe this is what you mean here, is that if new variables unit has to match the units here, because all Insight Maker is going to do is going to create a copy of new variable and put it here, but 5 seconds later. So if this new variable, maybe I should call this new variable 2 or something, just to keep things. So if new variable 2 has units of centimeters, then new variable better have length units in order to make this work. If new variable has math units and new variable 2 has length units, then I better multiply this delayed term by a conversion factor that converts mass into length or length into mass, whichever way direction I said there. So you just have to make sure your units are consistent. And in the case of delay, delay will inherit the units of whatever you pass it, but other functions may not. So functions operate differently just based on whatever they do. All right, any other questions? Great. All right, so that was the Insight Maker case. So it's not only, simulating things down the esophagus. What other things are fixed delays? Well, anything that sort of looks like schooling behavior. So like a tight cluster of animals moves coherently through a system, like fish that move in a ball together as they get from one point to another, cars that move in a ball together as they move from one city block to another, and so on. Those are typically modeled as fixed delays. Age, structure, and population, that's another one. So the students that go into first grade in primary school or elementary school typically are the same students that a year later are in second grade. There might be a little bit of leakage or whatever, but for the most part, if you've got 300 students in first grade, a year later, you'll have 300 students in second grade. And so age, structure, and population, those will often have fixed delays. So whenever we talk about cohorts, the term cohort implies a fixed delay. Whoever you see at one point, you'll see that exact same group at another point sometime later. Similarly, so that's what I mean, like school systems, that's the other one there. And then material flow, transit delays. So whenever you've got a bunch of things at point A, that sometime later, all of those things will be at point B, and new things will be at point A, then that matches the fixed delay model. It's not a fixed delay if some individuals at point A get to go to point B, while other individuals at point A have to hang back, and vice versa. So at the point where a bunch of individuals get separated out and kind of spread out so that some go faster and some go slower, then we have to use a different type of delay. And that's the next one we'll talk about, smoothing delays. But fixed delays, everybody's kind of moving together from one point to another. So any questions about those examples, what I mean by those? Okay. All right, so that was fixed delays, but fixed delays are probably not the most important thing in this hunger control loop. Probably the reason why you eat something and you don't immediately feel like a relief in hunger has to do more with stuff that's going on in the stomach. So we want to focus on the stomach, and that's where it gets us to introduce something called smoothing or averaging delays. And the idea here is that we have food that enters the stomach at some instant, but the actual nutrients enter the bloodstream much more slowly. So it's like you can imagine that the food's in the stomach and eventually some nutrients get in the bloodstream, but as the food gets processed, it takes a long time for all the nutrients to get into there. And then even when the food leaves the stomach, that's the sort of the trailing edge of this box, then there still are nutrients that are caught up in the lining of the stomach that are still being processed. And that's why you don't immediately see a drop to zero in, say, the number of the sugars in the blood, for example, because there's still some that we're in the middle of processing. And so eventually it drops to zero, but not immediately after this. So we refer to these as smoothing delays for a number of reasons. And one of the kind of obvious reasons is the input is very sharp and the output is kind of a smooth version. It's like we cut off the corner and rounded it off in both of these cases. We've smoothed it out. So, so that's kind of what I'm saying here. You should recognize this because this is exactly what goes on in the toilet bowl example. So it was like you got a change in the desired water level in the toilet. It went up to 15 centimeters, but the sluggishness of the system caused it to slowly rise to the 15 centimeters. And then if you, on the other side of the flush, when you want all of the water to go into the bowl, it might take a little bit of time for the actual water to get from the tank into the bowl. And so that's what we're sort of seeing here. Another smoothing delay, or an exponential delay is another term we use for it. And here, the delay term, so like the digestive efficiency in the stomach, for example, characterizes the sluggishness of the system, how much of a gap there is between the red line and the blue line. And so we can build a little toilet model, basically, that for any type of smoothing delay. And so I'll show you that there are shortcuts to this in Vensim and Insight Maker, but before we know them, I mean, behind the scenes in these shortcuts is this little module that, again, is gonna look a lot like our toilet model. So we have input, let's say food that comes into a stomach. We have the actual, nutrients in the bloodstream coming out of the stomach. And we've got some delay term, which is representing the connection between the two of them. And that's really the same thing as our toilet bowl model, where our input is kind of like the desired level of water. The average is the actual level of water. And the delay characterizes how quickly the valve works. So that's what I'm just sort of saying here. The input is the target height. The output is the actual water level. The delay is how sluggish the valve is. So, so that's one way you can think. Whenever I talk about smoothing delays, just think about the toilet model. And that's exactly what this little diagram is. It really is, input minus average. That's the tank gap divided by delay. That's the time constant for the toilet. Now I can take this same diagram, and because it's got a minus there, I can turn that into an outflow and turn it into this diagram, and it's identical. So both of these diagrams are the same thing, but this one helps me see this formula down here. This formula is what is going on behind the scenes inside Vensim or Insight Maker. And so it helps us understand better why we call this an averaging delay. So if we look down here, I'm saying that the water level, or the nutrients in the blood at some time are equal to the nutrients in the blood one time step earlier, minus, and then there's this outflow here, which is just the level that was in let's say the blood, the nutrients in the blood, or the water level at that earlier time, plus the input. So it's almost like there's a constant leak that has to do with, that depends upon how much water is in the tank, but there's an inflow, which is the desired water level. And so we're kind of sort of looking at this, well, it's, so it's whatever the current water level is minus this little bit of leak plus this input. That's one way to visualize what's going on with the smoothing delay. And if I focus a little bit more on this, then I can see why we might call it averaging. I can take this formula here, which comes directly out of this, regroup some of the terms so that they look like this thing down here. And this new version, which is identical to the version I just said, basically says that the water level at the next time step, or the nutrient flow at the next model time step in the blood, is equal to a combination of either the desired water level, or you could say the food that's in the stomach, and the previous water level, or the previous nutrients in the blood. And the delay term, how big delay is, tells you whether you're weighting this average to be more biased towards the input or more biased towards the previous values. So if the delay is very large, let's say I'll go the other way. If delay is very small, so delay is equal to dt, then this term goes to 0. And so the water level is just going to be equal to the desired water level immediately, or the nutrients in the blood flow are just going to be equal to the food intake into the stomach basically immediately. But if I go the other way and I say when delay is infinite, then now the input, effectively this thing gets killed because delay is infinite. And this thing becomes just the water level later is equal to the water level now, with no change from the input. So if you have an infinite delay, it's like the input's ignored. If you have a small delay, then it's like the input is taken on immediately. If you have any intermediate delay, it's a mixture, a weighted average of the previous water level, or the previous nutrients in the blood flow, and the desired water level, or the amount of food driving the system in the stomach. So that's another reason why we call it an averaging delay, is that instead of being a direct copy of an input sometime later, it's a mixture of the input now and the current level without the input now. And that delay tells you how much of that mixture. Right, so that's kind of the mathy thing behind why we call it averaging. The other way we can think of it is maybe simpler, is that delay, and this is like the time constant interpretation, can be viewed as kind of the average delay for a small unit of food. So if a bunch of food goes in there, some of the food is taken up into the bloodstream immediately, other food has to wait. If we were to look across all units of food in the stomach, then the average delay until they get into the bloodstream would be this delay term or this time constant term. That's another way we can view that. So it's an average delay. So it's another way, use of this term averaging. So, and that's what I'm just saying. Sometimes we call it the mean lifetime for these systems or a time constant for these systems. So are there any questions about these ideas? So I'm not worried too much about you being able to write out this expression from these things, but I do care that when we think about smoothing delays, that this delay term makes sense to you as a mean lifetime term or a time constant term, as an average amount of time that if there's a group of individuals that arrive, some of those individuals leave immediately, some of those individuals have to stick around for a long amount of time. The average amount of time that they wait is their mean lifetime or time constant. And that's the term delay that we put into this little unit here as this delay term. That's how we characterize the speed of these delays. So yeah. It's related to a half-life. So the question was, this is kind of like a half-life. And so time constant and half-life are identical concepts, but they're related by a natural log of 2. So if you know one, you can multiply it or divide it by natural log of 2 to get the other. So to put it another way, and I'll remind again, the time constant is the time until, if I got rid of the input, so the stomach is empty, I have to say how long until half the food, so if I get rid of half of the nutrients in the stomach, if I were to view that, if I were to go back to the curve that showed the exponential decay, I think it's right here, this will work. So if I think about this drop here, let's say food has now exited the stomach, and I want to see how quickly is that felt in the bloodstream. The time constant, or the average delay, is the time until this reaches 63% of a drop, or in other words, reaches about 37%. The half-life is the time until this reaches 50%. And so, but both of those terms, half-life and time constant, are built from exponential decay. And so it just turns out that if you know when the exponential is going to hit 50%, then you can multiply it by natural log 2, and you can find out how much longer you have to wait until it reaches 63%. And vice versa, if you know that it's reached 63%, if you want to know at what time did it reach 50%, then you just divide it by natural log 2. So that's how they're related. Any other questions, online or otherwise? Step through these again. Okay. All right. So when we talk about smoothing delays, I want you to get used to thinking about this term inertia, because this is a very powerful term that helps us describe the sluggishness of a wide variety of systems. And we think about inertia, we often think about Newton and Newton's second law, that force equals mass times acceleration. And so if we break down Newton's second law, it's just saying that a net force applied to an object produces a proportional acceleration in the direction of that force. Well, what he's saying here is if I push on an object, it will move, but the speed at which it moves is going to depend upon its mass. And so if it's a light object, I apply the one force and it very quickly will take off. If it's a heavy object, I apply the same force, it will move, but it'll move at a much slower rate. And so this mass, like we'll see, is going to relate to the sluggishness of that system. Mass is one way to talk about inertia in systems. So an object's mass represents the relationship between a force and its change in velocity. Higher mass objects mean the velocity doesn't change very quickly. lower mass objects, the velocity tracks the force that you apply. So if I take that and I, turned into this F equals ma form, so I just add a few, just change these into a variable form, then I can say, well, what is acceleration? It's the rate of change of velocity. So I can put that in here, and hopefully you see that this is going towards a stock and flow model. And I can rearrange that. So I can say that the rate of change of velocity is just the force divided by the mass. And now we can start seeing that the rate, it's like force is our desired change in velocity, and mass is just scaling it down. The more massive things are, it's just dividing down force to make it have less of an impact on velocity. And so if I were to write that in words, I'm saying the change of velocity is the force of the change divided by this mass term. And I can generalize that and say the change in any system variable is the force of the change on that variable. This is like the tank gap in the toilet model divided by the system's inertia. And I write it this way because I want you to see that the inertia doesn't have to just be in terms of kilograms. It can also be in terms of seconds. In fact, very often we characterize inertia in time units, like time constants and half-lives and so on. So that's what I'm sort of trying to gather or capture here, is that the change in output is the difference between desired and actual. That's like our tank gap divided by the system inertia. And so instead of using math, we can generalize and think across all systems in terms of delay. We can sort of think about how sluggish is this system in terms of how quickly does it respond to a force in change. And mass is a physical measure of inertia, but there are social inertias as well, and so on and so forth. And so I've got mass here as our physical example, but we can think of like another physical example, heat capacity. So water has a high heat capacity, which means that if I put water on a stove, it takes a while for the water's temperature to change. And likewise, when I turn the stove off, it takes a while for that water to cool down. Compare that to air. Very quickly, air can heat up, and very quickly, air can cool back down. It doesn't have a high heat capacity. So mass is one example of inertia. Heat capacity is another example of inertia. Something like bucket diameter is another example of inertia. As I trickle water into a bucket, the wider the bucket, the slower the water level rises in the bucket. The thinner is it turns into like just a test tube, then the same trickle of water causes the water level to change very quickly. And then we get into more abstract things like stubbornness. So I might need to model in a dynamical systems model certain populations and how willing they are to adopt an idea. And I know that there are certain populations that are maybe more skeptical than others. And I might need to model that and say, how much compliance am I going to need from this population to get a desired outcome? And what groups of the population are going to be more resistant to change than others? And that might, I might model it internally the same way I'd model F equals ma. But instead of using math, I'll use some parameter of how resistant they are to change, like their stubbornness, and so on and so forth. And so in general, when we talk about inertia, we don't just mean mass, we mean anything's resistance to an applied force is an inertia, or their tendency to keep doing the same thing they're doing, even though a force is being applied. So the flow into a stock, so for modeling any of these systems, we're probably going to have a flow into the stock is equal to a desired change in the stock, which might be a gap, divided by that inertia. So if we look at that, well, I just rearrange this thing, and the desired change in the stock is equal to the system's inertia times the flow into the stock. Well, let's see, that's just this, where I've multiplied both sides by system's inertia. If I look at that, that's just F equals ma. So F equals ma describes physical variables, but it also is a model we can use to talk about any sort of stubbornness in systems. And it could be toilets as well. So if we think about these toilets here, then input minus average, that's just like the tank gap. The inertia in the toilet, which is the sluggishness of the valve, is just this delay. So the flow into the toilet is just the tank gap divided by that delay. And this is just F equals ma, but we're just changing our definitions of what the F and the M and the A are, but the dynamics, they're identical. So that's kind of smoothing delays. So putting all that together, and hopefully this picture will help make things a little bit clearer about fixed versus smoothing. If we're thinking about a city transit system here, we might have a city block A, a city block B, and we've got a, so there's a stoplight at A, a stoplight at B, and then there's a straight line of road in between them. And both types of delays are represented here. So when cars are waiting at the intersection at A, we can model how many cars are entering the street block here using a smoothing delay. Because at the instant the light turns green, some of the cars, so that's like this input here, that's the instant the light turns green. You might think it's the desired number of cars is like suddenly all the cars you want in this block in between the intersections, but that's not what's going to happen. The cars on the front end are going to immediately get into the intersection. The cars on the back end are going to take a while, and the cars are going to spread out until they reach some steady state distance, and then they'll move together like a school. So that spreading out process represents this smoothing delay. But then once they are in the block, then any group of cars at the beginning here is probably going to be roughly together at the end. So we can model that with a fixed delay. And so this would be like if I had one car here, then a few seconds later, I'll have one car over here. And so if I have 6 cars here, a few seconds later, I'll have 6 cars there. So I can build systems in Insight Maker that have both of these delays together, some of them that spread things out, other ones that keep them together, but just add delay. So it's an example of how systems often have both, the same way we have the esophagus as a fixed delay and the stomach as a smoothing delay. So any questions about these delay ideas here? That makes sense that these are 2 types of tools we can use to model delays when we get down into it. Okay. All right, so now I want to show you how to implement those delays in a way that's simpler, those smoothing delays, and that doesn't require you to draw this every time. Fortunately, smoothing delays are so common that both Vensim and Insight Maker already have a function that implements them for you. So inside Vensim, you can go into the equations, and if you scroll down into the functions, they have a little function reference. It's down here, the bottom left of the equation thing here. You can find a function called smooth, and it takes input as the thing that you want as the thing that's being spread out. It's like the tank gap, and the delay. That is the time constant for the system. That is the average delay. So you just put that in there the same way they're put in when we drew that whole large diagram out. And then you can also specify an initial condition if you want, and that's that smooth I with initial condition. But smooth by default just takes those 2 parameters, just like this one. Pretty simple than that. So as an example of that, if I drew this diagram here where I've got input, this is like the rate into the esophagus, and this is like, this is like the input, this is like food into the stomach, and this is like nutrients into the bloodstream. Then I would have just smooth where this is food into the stomach, and that's the average amount of time it takes for a unit of food to turn into nutrients into the blood, is like 2.5, and that will implement this smoothing delay. That's how we do it in Vensim. So, and that's where we go, that's on there. So any question about the Vensim one? Does that make sense? It's just another function. Instead of delay fixed, we use smooth. If we did delay fixed, we get an exact copy of the blue one 2.5 seconds later. If we do smooth, we take these boxes and we turn them into these kind of shark fin looking things. Okay. All right. It's just like, so basically what's interesting about this is that that smooth is basically the toilet tank assignments that you did. Basically the whole thing is now one, like you could redo the toilet tank assignment just using this function. So, if you knew, this would be the desired target minus level, you could put that here. This would be 1, because I told you to do like a time constant of 1, and that's your toilet model right there in a single line. Okay. So what you see here is something that we're going to call a step response. The input is this blue line that jumps up, it looks like a step that you'd step on, just go straight up. And the output is this response here. And so we will use real systems to characterize how fast or slow they are. So in order to figure out what to put there, we often will go into a real system and force it through this experiment and see how quickly, for example, the water level rises. And what we do then is this goes back to our talk about time constants. We look at, if we give you an input step, at what time point does the output reach 63.2% of the full scale of that step? And in this case, it's 2.5 seconds. And so I would say that the time constant here is 2.5 seconds, and that's where I would put 2.5 into this smooth inside Vensim in order to calibrate this to match the dynamics of the real world. So we do step responses in the real world to figure out what these smoothing delays are that we can then put into our models so that they're matched to the real world. So any questions about this? What do I mean by a step response? Okay. And then, like I've been saying, this delay is also called the time constant, which is often used when talking about step responses. So because I just want to make sure we get to higher order smoothing, I'm not going to make this an attendance exercise, but we can do this in class here. So if there's a green line here, it starts at 1, goes up to 1, and then there's this blue line here, and you can see this is 0 and this is 100% here. And so the question in here is, if I were to say this came from a real system, where this is the step that we put into a real system, and this is the response the real system gave us, then what would be the time constant that we would read out of this system? Anybody have a guess at that, or can read it from here? So I can show you this is about 50% right here, 60%, 70%, 80%. So just so you know, those are those there. Yeah. It is in months, right? That's one. So you said 3 here. Now, did you say that because is that because it's that's where it hits about 63%? That is one good answer. The 3 months here, but there's a trick here. Yeah, go ahead. Almost. So they're kind of going in the line of thinking here. Well, we would so the number we would say that the step input starts at 1, and it is true that at time 3 it hits 63%. I think I heard somebody else say it was 2. Yeah, I would say that the step. Oh, I didn't have it. I would say the time constant here is 2, because you're right that it does at 3 seconds is when it hits 63%. But we don't actually hit the system until time 1. So you ring the bell at time 1, and then you start the clock at that point. And so it takes 2 seconds after we hit it with the step to reach the 63%. So we would put 2 up here. Does that make sense? Okay, great. Questions online or in class? All right. So I want to cover how Insight Maker does this, and then get to higher order smoothing, because I think that'll come up in the bonus on the homework. So Insight Maker also has a smoothing shortcut, because it's just super common to implement smoothing delays in these systems. And so likewise, you go to historical functions and you go down here and there's a function called smooth, and it works very similar to Vensim. So you take input as the first argument, time constant as the second argument, and then an initial value, which you can set equal to 0. And I think Vensim or Insight Maker will actually let you drop it as an so you don't need it. So yeah, this is optional there, is all I'm saying there. And so we basically do exactly the same thing that we do in Vensim. And so I can implement with smooth the same thing that I implemented in Vensim. All right, so nothing new there, exactly the same term. Okay. All right, so we want to finish up here with a couple of slightly more advanced topics, but topics you should know about. So I mentioned step responses. Well, I already showed you at the beginning of class how to generate a pulse in Vensim or Insight Maker. You can actually generate a step too, because step responses are super common in dynamical systems models. In Vensim, there is a command called step. So you can create inside any variable, you can put step, and that variable can act as sort of as an input to your system. So you can just have the variable sitting out there with no input, and it will be like a constant that has two levels. Up until this time of step, it will be the low level 0. And then at time of step, it'll jump up to whatever you put into height here. Insight Maker's got the exact same thing, but they switch the order of the arguments. And so time of step comes first and the height comes second. So it's the same step, but they just flip the order. So just be careful about those things and plot, like when you're debugging these things. This came up, I think somebody asked about how do you debug these things and know your functions are doing the right thing. This is in the muddiest point. And a lot of times you just have to set up useful inputs that kind of exercise or exorcise the system, and then look at the outputs of the things they're going into and make sure they make sense. So with that step, so if I wanted to generate a step response, I could do that in both of those. So that's the one thing. So any questions about this? It's just like I showed you, you can do pulses. This is like a pulse, but it doesn't ever go back down. So you can just set the edge of the pulse and then it just stays up forever. So it's a way you can do that in both. That way you can do step responses yourself. The other thing I want to talk about here is higher order smoothing. So I've been giving this analogy to a single stomach, one large smoothing delay. But now I want to extend that analogy to an undulate, to something like a cow here that has multiple stomachs. It's a ruminant. It's got these, food not only moves from one stomach and then on down, it has to sit in multiple stomachs before it actually kind of hits the intestines. So the idea here is, here I had one smoothing delay. Imagine if I broke this one smoothing delay into 3 smoothing delays that individually had a third the time constant, then collectively have the same average total delay. So it's like this is a faster stomach, significantly faster because it's got 33% the time constant, but you got to go through 3 of them. So when you look at these two, it looks like they might be the same, but in reality, each individual stomach is so much faster that there's less spreading out in the delay in each individual stomach. And so overall, when you add them all together, you get much less variance in the delay when you go through 3 fast stomachs than 1 slow stomach. And I'll show you what that means here in just a second. And if you add even more stomachs, so now I've got 6 stomachs where each one of them has a time constant that's a 1/6 of the original time constant, this is going to happen even more. So I hope you can kind of see that once this becomes the original time constant divided by like 100, then effectively each individual stomach just rises immediately. It doesn't really have any smoothing effect. It just jumps immediately back up. And if all of these stomachs are jumping up, then when you link them all together, then they will have the same average delay as this stomach, but they'll basically sit at 0 and then jump back up. In other words, this is going to be an approximation of a fixed delay. So adding smoothing delays in series like this makes them look more and more like fixed delays. So let's see what I mean by that. So if I've got a plot here where I've got a step response going in, that's the green line here, the step. And then I've got this blue line. This is a first order smoothing delay, our standard smoothing delay that we've been talking about. It just rises very slowly. But in Vensim, and Insight Maker's got something like this too, there's something called smooth 3, which is a third order smoothing delay. What smooth 3 does, I've got down here, is it just takes the normal smooth function and it takes whatever delay you give it and divides it by 3. But then it passes that into another smoothing function with delay divided by 3, and then that into another smoothing function with delay divided by 3. It's like having 3 stomachs with a third time constant, like I have over here. And the effect is you get this inflection point, this red curve here. Notice that it doesn't start quite as fast as the blue curve, but then it speeds up and overtakes the blue curve. So it becomes a little bit more like a fixed delay where it's slow and then it rises quicker. I can go even farther with, in Vensim, it's called smooth in, and you can actually put whatever the in you want here. So if I put 3 there, it acts like smooth 3. If I put 1, it acts like smooth. If I put like 20, it acts like a chain of 20 of these smoothing delays where each have a delay divided by 20. And when I put that in there, then I get this green line, and this green line is almost vertical. So it almost looks like a fixed delay version of the step here. So all 3 of these have got, basically a 2-second delay, but the first order one, smooth, it's spread out. So you get an immediate response and then it hangs around for a long time. Whereas the 20th order one, it sort of doesn't respond until almost 2 seconds of delay, and then it jumps up almost vertically, and then it settles down almost immediately. So if this 20 was like a 200, this would pretty much be a fixed delay. The reason we have these is that the real world is not always going to act exactly like a nice smoothing delay. And the real world is not always going to act exactly like a fixed delay. This allows us to look at our real world system and say, you know what? The response to this system is sluggish, but it's not quite this sluggish. It gives us more ability to adjust the sort of slope of these delays to make things somewhere in between a fixed delay and a smoothing delay. All right, so there are questions about that. You see what I mean by higher order delays change the kind of slope of the smoothing delay so that it gets more and more and more like a fixed delay. Questions online? Okay, great. So most simulation packages have a smooth as well as a delay, and it gets a little confusing because you'll say like, I'll see smooth and delay. Vensim's got both, smooth and delay 1, smooth 3 and delay 3, smooth in and delay in. For our purposes in these class, these functions are identical. Smooth is identical to delay 1. When you get into more advanced cases where the delay can itself change over time, then these delays functions start acting differently. But for us, if you happen to see like delay 1, delay 3, delay in, and then smooth 3 and smooth in Vensim, and you're wondering what's the difference there, for our purposes, there is no difference. You can think of it as synonyms. And I think that's all I've sort of got here. So any questions about delays? This is like our last major add-on to Vensim and Insight Maker. The next homework will kind of allow us to maybe talk about a few more sophisticated things, but this is pretty much it. So now at this point, it's all kind of case studies, seeing how to use these things and build the formulas for them, the equations and stuff like that. Questions online? Make sure there's no questions on the other form. Okay. All right, so just reminders, this is lecture E2, so we'll have E3 on Thursday, and then E4 will be a week from today. So a week from today, make sure to read chapter 6. If you're interested in delays, you might want to skim over chapter 4, but we'll skip over 4 and 5, so read about 6. Muddy's Point, of course, we do this week. Reading exercise, like I said, Tuesday. The final project proposal. So now that all of the groups are formed, then this we're looking for Sunday, basically this Sunday, as a group assignment. So only one group member needs to submit a short. It's like a 2-page kind of proposal where you tell me roughly what system you're trying to model, what's the general motivation for that system, like in paragraph form. And then you can in list form say, and these are sort of some dynamical variables we think are important. And then say like things like, and here's a causal loop diagram that shows for some of the variables that we picked, how we think they might influence each other. I'm not expecting you to list every variable that you're going to put on your model, but I want you to show me evidence that you've picked a system and you've started thinking through how you're going to quantify the investigation of that system. So what, and the key thing is, what are you really interested in studying, and how is simulation going to tell you something that just thinking about it doesn't do for you? So, we really need someone to say like, I have a question that I really can't get good answer to unless I start simulating it. That's what I want you to try to put into these proposals. And then I'll read through all those, see if things are way too ambitious or maybe need a little bit more complexity, and get back to you right after you turn those in. And then we've got this assignment E2. It's got 2 parts, one that's kind of the previous lecture and one that's this lecture. It's not due this Sunday. It's not due until the Sunday after lecture E5. So you got quite a bit of time to work on this one. All right, so I'm happy to take any other questions, but let me give the attendance exercise, and I'll then let you guys go. If I can manage to get my mouse back. Here we go. So the question I have here is a high order smoothing delay like smooth 20 is similar to what other kind of delay? So I was saying that higher order smoothing delays help us move from one type of delay to another. So what is a higher order? What is a very high order smoothing delay like? What other type of delay? And that's all I've got for you. So if you have anything else, feel free to come up. Otherwise, we'll see you on Thursday. All right, looks like most people have disconnected from online. So I will think about ending the meeting unless there's any other questions. All right, see you Thursday.